This video is going to illustrate the use of design graphs through a study case. We're going to take interest in an hydraulic actuator, such as a spoiler actuator. For the rest of the example, we will limit our study to sizing of the servo jack association. It is necessary to establish beforehand all the design parameters and objectives that come from technical specifications and that will help us during the design stage. These parameters can be obtained by listing the requirements of the system and transforming them into useful parameters in our design stage. In this example, we will keep in mind specifications represented by numerical values that must be respected, the jack's operating point, effort, speed, the necessary stroke, the stiffness of the structure the actuator will be fixed on, the pressure of the hydraulic network. And objectives are constraints such as a maximum effort that mustn't be exceeded so that we don't damage the control surface, an hydraulic flow to minimize in order to limit the impact of the actuator on the network's total mass. What's left is going to allow us to link these major attributes of the specifications to the components. Here are all the equations related to the quantities previously stated, and that link them to the component's characteristics. Equation 1. The maximum effort on the jack is obtained at null speed. Equation 2. The jack's stroke must take into account both the required stroke and the structure's deformation under a certain load. Equation 3 and 4. The transformation from effort pressure to speed flow executed by the jack. Equation 5. The nominal flow of the servo valve is linked to the torque, pressure or flow, at the operating point. Equation 6. The maximum flow consumed is obtained when there is no effort exerted on the jack. The 6 equations are now graphically represented. They link the data obtained in the specifications to the component's characteristics. At this point, the edges of the graph are not oriented. Specifications, represented by numerical values, are to be respected. There are data in our sizing procedure. They're represented with triangles and allow us to give an orientation to the corresponding edges. Equation 2 engages all the necessary quantities to compute the output C. Equation 3 has to respect constraints. By considering that the value of P0 is already known, we are then able to calculate the area S. The same way, by giving a value to the pressure difference dP num, it is possible to determine all the other values of the problem. Notably, the objectives and constraints stem from the specifications, represented here as hexagons. Those equations can be represented on an n-squared diagram. Inputs, originating from requirements and the design hypothesis, are located on the upper side. For every computation, inputs are sorted in vertical lines, the outputs, on the other end, on the horizontal lines. We can detect here an algebraic loop between computation 1 and 3. As maximum effort requires to compute the area S, it is therefore necessary to calculate S there so that we avoid this algebraic loop. This oriented graph enables us to define all the computation steps to follow in order to size the aggregate servo valve jack. They're easily implemented in a calculus software, such as a spreadsheet. The Excel downloadable file that can be found on Moodle is an example about how to implement the calculus procedure and how to use it with the solver to optimize the configuration. The independent variable is the P0 pressure. The quantity that has to be optimized, and in this case minimized, is the maximum flow. One constraint about the maximum effort has to be respected. You can deduce here that using a P0 pressure equal to 140 bars is the optimal solution. We can therefore determine the jack on its operating point corresponding to a pressure equal to 2/3 of the network pressure if we want to minimize the maximum flow. This result could have been obtained in an analytical way, but allows us to illustrate the sizing process in this case.